Yes, I will start the lecture now. So for revision purpose, I'll solve one example which we have already done in the previous, on the type which we have already done in the previous lecture. Evaluate integral 0 pi by 2 0 to y 1 minus e square sin square x. So we can see that this is the value of y, and y is constant, so strip is parallel to x-axis. So given strip, parallel to x-axis, for which the limits are y is equal to 0 to y equal to pi by 2. X is running from 0 to x equal to y. Let's draw the diagram for the same. X equal to y, a straight line passing through the origin. X is running from 0. If you look at values of y is equal to 0 to y equal to pi by 2. Y equal to pi by 2 is going to be this. So since the strip is parallel to x-axis, the region which is bounded is this. So we can see that all the conditions are satisfied here. Y is running from 0 to y equal to pi by 2. This is the line y equal to pi by 2. The left hand side end of your horizontal strip is x equal to 0 to the line x equal to y. Now consider the strip parallel to y axis. Consider the strip parallel to y axis. So the point of intersection here is going to be pi by 2 comma pi by 2, as this is the intersection of the line y equal to pi by 2 with the line y equal to x. So in this case, now I will have to fix the value of x. X is running from 0 to x equal to pi by 2. Y is running from the line. The equation of line is y equal to x. So y is running from x to y equal to pi. So by the change of order, what we get is 0 to pi by 2, x to pi by 2, cos of 2y under root 1 minus a square sin square. And the order is going to be dy dx. So the first integration is going to be with respect to y. So this under root 1 minus a square x square will become constant. So 0 to pi by 2 under root 1 minus a square sin square x. The integration of cos 2y is sine 2y by 2 from x to 5 by 2. So this will be equal to 0 to 5 by 2 under root 1 minus a square sine square x. You put the upper limit sine pi, that is going to be 0. So at upper limit it is 0, and at the lower limit what we get is minus sine 2x. Minus sine 2x divided by 2 t. But now we can see that the derivative of 1 minus a square sine square x is can be adjusted actually, or that can be written as a sine square x can be substituted as t, and we'll have under root of 1 minus a square t. So that is the another way of doing it. So 1 minus a square sine square x, if we put that as t minus a square sine square x is equal to t, then the derivative is going to be minus 2 a square sine square sine x into cos x dx equal to d. So derivative we can adjust there and substitute that under root t. So put- so integration 0 to pi by 2 under root of 1 minus a square sine square x. So what we need is the sine of 2x can be written as 2 times sine x cos x. So multiply and divide by a square. So this will be minus 2 a square sine x cos x. I will write this. Sine x into cos x dx. So the derivative of 1 minus a square sine square x is here minus 2 a square sine x cos x dx. So simply what do we have is the integration of under root of t. So integration of root x is actually 1 upon 2 root x. Am I right? Not. T raised to 1 by 2. So 1 by 2 plus 1. So 1 minus a square sine square x raised to 3 by 2 upon 3 by 2. Integration 0 to 5 by 2. So we'll have 1 upon 3a square when we put the upper limit. So 1 minus a square sine square pi by 2. But sine pi by 2 is 1. So we'll have 1 minus a square raised to 3 by 2. 1 minus a square raised to 3 by 2. And when you put this as 0, so we'll have minus 1. That is the final answer. So this type of examples we have actually seen in the previous lecture, and I said that in the next lecture solve some different examples where we actually need to just separate the region. So the first example on the same we are going to solve is change the order change the order of integration 0 to 5, 2 minus x to 2 plus x, f of x comma y dy d. So we just need to change the order. We don't need to actually evaluate the integral. So we'll collect the given information. So x is used in the next integral. So x is running from 0 to 5. So these are the limits for x. These are the limits for y. As x is constant, so given strip parallel to y axis. Given strip is parallel to y axis. X is running from 0 to x equal to 5. Y is running from 2 minus x to y equal to 2 plus x. Just for simplification, I'll make the simplified equation of the two lines. So one is x plus y is equal to 2, the first one, and the other one is x minus y equal to minus 2. Let's draw the diagram. As I said, diagrams are going to play a vital role here in order to give the new limits. Now x plus y is equal to 2. So if you put x equal to 0, you will get y equal to 2. So the point is 0 comma 2. If you put y equal to 0, you will get x equal to 2. Join these 2 points. This is the first line, x plus y equal to 2. For x minus y equal to minus 2, if you put say y as 0, so x plus y equal to 2, y x minus y equal to minus 2. So if you put y equal to 0, then x will get minus 2. Y is equal to 2 plus x, y minus x equal to x equal to 0. Fine, it is correct. So the 2 points that we get here are put y equal to 0 and get x equal to minus 2, minus 2 comma 0. If you put x equal to 0, you get y equal to. This is the another line. This is the line x minus y equal to minus 2. Now next thing is we look at the value of x. A strip is parallel to y axis, the vertical one. But you can see that for a vertical strip, what do we have is we have this lower limit as the first line, and the other one that we have is lower limit is x plus y equal to 2. This line is our lower limit, and x minus y equal to minus 2 is the upper limit. So the strip has to be here. That is what we conclude from the given information, as the lower limit is this line x plus y equal to 2, and the upper limit is y is equal to 2 plus x. Now our x is running from 0 to x equal to 5. So x equal to 5 may be lying somewhere here beyond that. This is the line x equal to 5. So this is my region R. Now I want to change the order. But when I'm going to change the order, I will have to consider a horizontal strip. But if I consider a horizontal strip, beyond this point, you can see that our left-hand side limit will change. This point is 0, comma 2. Once we have a strip in this region, our limits are going to be different. It will go from this line, which is x plus y is equal to 2, to the line x equal to 5. Whereas in this region, our left hand side limit is going to be x minus y equal to minus 2. So we'll have to divide the region in two parts, R1 and R2. So consider the strip parallel to x-axis. So note that the limit for x changes after y is equal to 2. So after the point y equal to 2, the line y equal to 2, our limits are going to change. So what we do is we divide the region in two parts. So divide R in two parts. R1, which is below y equal to 2, and R2 above y equal to 2. So we are going to give the limits in two parts now. So consider the lower triangle. So I'll shade this region. So this is a region R1. And the above region is R2. We'll have to give the limits for both the regions separately. And this is R1, this is R2. So in R1, what do we see? We'll have a horizontal strip parallel to x-axis. So for the strip parallel to x-axis, there will be an intersection of x equal to 5. So 5, comma, the value of y has to be minus 3. And what about this point? This point will have 5, comma. The second equation, if we put x equal to 5, so the value of y is 7. So in R1, x is the y is running from minus 3 to y equal to 2. And the value of x in this region is going to be from this line. The equation of line is x plus y equal to 2. From that, the value of x is going to be 2 minus y, 2, x equal to 5. And in R2, if you look at R2, the value of y goes from 2 to y equal to 7, and the value of x goes from this line, this one. From that, the value of x will be y minus 2 to x equal to 5. So once all of these things are clear, so substituting, so hence I is going to be integration minus 3 to 2 2 minus y to 5 f of x comma y. The order is going to be dx dy plus, now this has to be the other region, 2 to 7 y minus 2 5 of x comma y dx dy. This is the changed order. If you have any difficulty, you can ask, or I'll go ahead.
So how did we get that 5 comma 7 and 5 comma minus 3? The minus 3 and 7.
You put that x equal to 5 in the equation of line, you will get the point of intersection. It's just the intersection of two lines.
Ah, okay, okay, got it.
So express the following as a single integral. Express as single integral. The first one, integration 0 to 1 minus root y plus root y dx dy plus 1 to 2 minus 1 to plus 1 dx dy. So you can see that the order is dx dy. What the values of y are there in the first integral. So I'll call this I1 and this is I2. Another thing to notice is the integrand is the same, so we can actually combine them. So in I1, our limits are y is running from 0 to y equal to 1, x is running from minus root y to x is equal to plus root y. Note that the strip is parallel to x-axis in I2. Y is running from 1 to y equal to 2. X is running from minus 1 to x equal to 1. So we'll combine this. This is our region R1. This is our region R2. This given strip parallel to given strip parallel to x-axis. So we'll draw the diagram over here. So combining these two equations, what we have is y equal to x square actually. So y equal to x square is a parabola like this. So I'll mark 2 points. On given strip parallel to x-axis, it's a horizontal strip. So what happens is from y is equal to 0 to y equal to 1. So say this is y equal to 1. This is your R1 region. We can see that both the conditions are satisfied. Y is running from 0 to y equal to 1. In the horizontal strip, you can see that the strip is from this end to this end. Okay. This is the horizontal strip. Then in I2, what is happening is from y equal to 1 to y equal to 2. This is y equal to 2. The x is running from x equal to minus 1 to x equal to plus 1. So we'll have a straight line like this over here. which is x equal to -1, the straight line over here, which is x equal to +1. So what is happening? Beyond the point y equal to 1, our strip starts from x equal to -1 to x equal to +1. Okay, so I'll draw this line over here. And I'll shade the region. So the below region is this. Which is the I1 is representing, I1 is calculated over this region, whereas I2 is calculated over this region. Now what are we supposed to do is we need to change the order, and after the change of order we can see that the lower limit and upper limit of this integration is going to be same. So given strip is parallel to x-axis, so I'll consider the strip parallel to y-axis. So consider the strip parallel to y. So if I consider a vertical strip like this, so the strip is going to move from, so if I take a vertical strip, I need to fix the value of x. So x is running from -1 to x equal to +1. So you are going to move this horizontally from x equal to -1 to x equal to +1. Whereas the value of y is going to be from the parabola to the line this y equal to 2. So y equal to x square to y equal to 2. So and hence the combined integration is going to be, hence I is equal to integration -1 to +1 x square to 2 dy dx. This is the combined integration.
Sir, hello.
Yes.
Sir, can you explain that the graph part again? I didn't understand that. I didn't understood about this parabola. Hello.
Parabola. Yes. Parabola, you can combine these two equations, na? X equal to root minus root y and x equal to
Okay.
root y.
Okay. Yes, sir. Got it. Got it. Thank you.
So that is the that was the last example actually from the change of order. So the next example will introduce you to another aspect of this double integral, and the example is we need to evaluate this integral 1 minus x square. Zero to 1 integration 0 to under root 1 minus x square y square dy dx. So you can see that x is used in the next integral. So these are the values of x. This is the value of y. So the given strip is parallel to y axis. X is running from 0 to x equal to 1. Y is running from 0 to y equal to under root 1 minus x square. We can simplify this equation, and what do we get here is x square plus y square equal to 1. We know what is this. So this is a, what is this? X square plus y square equal to 1.
Circle.
Circle. So it is a circle of radius 1 with the center at origin. And you can also observe that this is the first example in the double integral. We have got a circle. And now we are trying to identify the region. So x is running from 0 to 1. Look, x is not taking the negative values. Given strip parallel to y-axis, parallel to y-axis. The strip is parallel to y-axis and x is taking just the values from 0 to 1. And you can see that the lower end of the strip is at y equal to 0. So y equal to 0 is x-axis. So lower end is on this line and this is the region over which you are evaluating the integral. Shade the region again. Only this much part is your part where you are integrating. So if you want to identify this, you can actually check out the limits. How do you check out the limits? We know the strip is vertical. Once we are confirmed that the strip is vertical, I will look at the lower end of the strip. Lower end is on y equal to 0, which is nothing but the x-axis, and upper end is on this circle. So this much. Another thing is our x is going from 0 to 1, so it is just the part of circle in first quadrant. Fine. Now this is what I want to evaluate. But you can see that if I directly go for integration over here, what we are going to get is 0 to 1. First of all, integration is with respect to y. So this will be y cubed by 3. Limits are from 0 to root 1 minus x square dx. So this will be 0 to 1 x square 1 minus x square raised to 3 dx. Again, this integration is very much difficult to solve, but you can find out a easier way. Yes, anyone? We put x is equal to sine theta. So this will become 1 minus sine square theta cos square theta, and under root will get cancelled out. So limits are going to be 0 to pi by 2 sine square theta cos cube theta. This will be cos theta d theta. Now this you can solve using reduction formula. This is one way. So we want to explore another way where, so this is a center, I mean circle with center at origin, and things are very much easier here. So that can be solved easily, but we need to solve complicated examples where this kind of adjustment is not possible. And for that purpose, we'll put x is equal to r cos theta, y is equal to r sine theta. What is this? Anyone? X is equal to r cos theta and y equal to r sine theta. What is this? Have you seen this somewhere? X equal to r cos theta and y equal to r sine theta. You haven't seen it anywhere? Adarsh
Yes, sir.
Tripathi, have you seen this anywhere? X equal to r cos theta, y equal to r sine theta.
Yes, sir.
What is it?
Parametric form of circle.
Parametric form of any other
Parametric
name?
form. Sir, it is for ellipse, I guess.
For ellipse. So
Sir,
these
it is
are
for-
pole. Yes, Sumit.
So it is for circle, I guess.
Anyone else have anything to speak?
It will form a circle of radius 1.
Are you sure?
Circle of radius r.
Circle of radius r. Yeah.
Circle of radius r, right?
So this is actually these are actually the polar equation. This is the polar form. We have gone through this. This is the polar form, polar equation. Okay, and in this, the r represents the distance from origin. Polar coordinates, you are well aware of the polar coordinates. And what are the polar coordinates? In polar coordinates, x is substituted as r cos theta and y substituted as r sin theta. In this, the r represents the distance of the point from the origin, and the theta represents the angle with positive x-axis. Angle with positive x-axis.
So, by this double integration, we are like finding the area of that quadrant of circle, na?
No. Double integral is actually used to find out the area, but in this case, the integrand is different. This x square y square, because of this x square y square, you're not actually finding out the area. I will come to this later. Right now, the theta represents the angle with positive x-axis. So we need to come back to our diagram. So this is the area over which you are integrating. So from the area, can you tell me what is the value of r in your area? What is r? R is the distance from origin. And what is theta? Theta is angle with positive x-axis. So you need to look at your region. In that region, you have to think what values r can take.
Sir, R will vary at every point.
Yes. So what is the range, Adarsh? Exactly, it will
Sir,
vary at
X
every
equals to 0 to 1 and Y equals to 0 to 1.
No. My question is, what is the range for values of r? You said that r will vary for each point. I want the limits in terms of r. What is the minimum value that r will take in your region, and what is the maximum value of r that will be in your region?
-1 is the minimum and
No.
+1 is
No.
So 0 is the minimum and 1 will be the maximum.
Yes. And what about theta?
Sir, 90 and 0.
No. You don't go from 90 to 0. You go from 0 to 90.
Yes, sir, 0 to 90.
Yes. So r in our region, the value of r will go from 0 to r equal to 1. The value of theta goes from 0 to pi by 2. So what do we think of is, we look at the region, and in that region we see that what is the distance in which the value of r is varying. So we can see that the r is going to be 0 at the center, and at the end of your region the value of r is going to be 1, and theta in our region is varying from 0 to pi by 2. So how do we actually identify this? And to identify this, I'll tell you a simple technique. when we are in polar coordinates, what we do is we draw the strip which is starting from origin and ending at the curve. So we draw a strip like this. So now we look at the strip. So strip starts from origin. It means that the value of r is 0 and it ends at the circle. The equation of circle is x square plus y square equal to 1. So you put x equal to r cos theta, y is equal to r sin theta and solve. You will get r equal to 1. So we can see that the value of r is going from 0 to r equal to 1. Now how you are going to move this strip? This strip is going to move like this in the anti-clockwise direction, and we can see that at this line theta is 0 and at this line theta is pi by 2. We have studied well enough in tracing of the polar curves that x-axis is theta equal to 0 and y is theta equal to pi by 2. So we have changed the limits. So r is running from 0 to 1, theta is running from 0 to pi by 2. What we substituted, x is r cos theta. So this will be r square cos square theta. The value of y is r square sin square theta. For time being, just assume that this dy dx is replaced by r dr d theta. Later I'll tell you why this is so. Now I want to solve this integration. R square, r square, r. So r raised to 5. You can see that this integrand can actually combined as r raised to 5 cos square theta sin square theta dr d theta. Lower limit, upper limits are constant. So what is the benefit? How can we solve this? We can separate the integral as per our remark 0 to 1 r raised to 5 dr, as the limits are constant and integrand can be written as the product. Theta is equal to 0 to pi by 2 cos square theta sin square theta d theta. R raised to 6 by 6. So we'll have 1 by 6. By reduction formula, this integration will be 1 into 1 upon 4 into 2 and pi by 2. Eight into 6 and whatever. So final answer, I'm not actually worried. So what we have done new in this example, so the new thing that we have done is I have converted the given Cartesian equation. Look, when you're studying in geometry, each point can be named differently. I mean, there are two ways of naming each and every point. One is Cartesian coordinates, and the other one is the polar coordinate. Okay, coordinate. In Cartesian coordinates, each and every point depends on its distance from x-axis or y-axis. Okay, so the x coordinate actually depends on the distance from y-axis, and y coordinate depends on the distance with x-axis. And in polar coordinates, what we do is each and every point is named by two things: its distance from the origin and its angle with positive x-axis. So these two things gives the name to this point in terms of r and theta. So some equations are better learned in Cartesian coordinates and some are better in polar coordinates. Like circle is always better in polar because r equal to 3 or r equal to 5. These things represents a circle. Whereas if I want to write a parabola in polar coordinates, it will become quite difficult. Okay, So earlier what we studied was in Cartesian how to find the double integrals by changing the order and solving the integration, how to give the limits. In the next lecture, what we will see is how to find the uh, integration in polar coordinates. If we have some integration in Cartesian coordinates, how can we convert it to polar, and how can it be solved later? Just one thing I want to clear in this example, particular example, this is exactly the process that we are going to do. Whatever integration is given, once it is circle or something like that, I'll put x equal to r cos theta, y is equal to r sin theta. This is the substitution to convert Cartesian to polar. And when we do this, when you change the when you make the substitutions in multiple integrals, in double integral, the idea is dx dy is replaced by Jacobian dr d theta. In your M1, you have seen what is Jacobian. So if x is equal to r cos theta, y is equal to r sin theta. This is the substitution that you are making. Then dx dy is replaced by Jacobian dr d theta. So anyone, what is Jacobian? What is the Jacobian that you have seen in your LADC course? No one knows what is Jacobian? Dabba of xy with respect to r comma theta, which can be solved further as determinant derivative of x with respect to r, derivative of x with respect to theta, derivative of y with respect to r, derivative of y with respect to theta. So this is the formula for Jacobian. But anyways, if you don't remember that, nothing to worry about. The Jacobian for polar coordinates is always r. Okay. So whenever you are going to transform a Cartesian equation to polar, then dx dy will be replaced by r dr d theta. Okay. So this is the idea. So to convert a given equation or the given integration which is in Cartesian form to a polar form, what you are going to do is you are going to put x is equal to r cos theta, you'll put x is equal to r sin theta, then dx dy you will replace by r dr d theta, and you will give the limits for r and theta depending on the diagram. So with this last remark, we'll end the lecture. And the remark is conversion of Cartesian to polar double integral. But the first step, draw the graph, as it is very important if we want to give the limits. Second, put x is equal to r cos theta, y is equal to r sin theta. Third one, replace dx dy as r dr d theta. And the fourth one, is from diagram. give the limits of r and theta. General idea is generally theta is constant. Theta is constant and r we get in terms of theta. A very important remark. In the next lecture, we'll see how to give the limits. Also, we'll solve the example, and hopefully the double integral will be over in the next lecture. Fine. Your marks are already mailed to you for the test that you have given on Saturday. You can check your mail.
Sir, which one actually? The MIT one or the personal one?
Whatever mail you used to give the exam, the same email ID will get your marks.
Sir, we didn't get any mail.
Check your mail. You may have got it. I have released the marks before.